Welcome to a new episode on the Technomora channel. We really hope you will enjoy watching it and invite you to tell us what you think of it by leaving your reactions below the video. And now, please allow me to present your host, Technomora.
Thank you, Julie, for that nice introduction, and welcome, dear viewers, to the second installment of building a symmetrical, regulated, and variable power supply. Now, in part 1, link below the video, you saw me build a symmetrical power supply which is capable of delivering 53 volts DC, either positive or negative, at 1 amp power output. Now, I also promised that I would build a few more functions that can be built into the power supply, and the prototype of the next function is right there on my workbench. And it's in fact what people would call a AC zero crossing detector. What is a zero crossing detector? Well, as you all know, AC power, which you get at the power outlet or at the output of a transformer, so at the secondary of a transformer, has a sinusoidal waveform. Alright? So pretty much as I drew here. Now, a sine wave will cross at several points, at least on the diagram, the 0 volt point, where in effect power, or I should say current, and voltage are both 0. Alright? And these are the points where that happens. Now, what I effectively built was a little device which detects when a full wave AC crosses the 0 volts level, which is depicted here by the x-axis. Alright, so 0 volt is here, and let's say for convenience the voltage peak to peak of this AC wave, sinusoidal wave, is 53 volts peak to peak. Now, it could be more, it could be less. It's not that critical. What really interests us is when the AC crosses the 0 point, so the 0 volts point. Now, some of you might ask, okay, but why would you want to detect when the AC crosses over from, say, positive, which is this part here of the wave, to 0 and then to negative? Why would you want to detect that point? Well, a lot of equipment is being turned on or off at exactly that point. So equipment, of course, which is AC powered, okay? And the reason for doing that is exactly because current and voltage at this point are 0, which means that, for example, the switch, or an electronic switch in this case, would get very little load from either switching on or off the appliance, and in fact the appliance would get a much softer startup if you switch it on at the 0 point. Alright, the same thing for switching off, of course. Yeah, it would get a far less abrupt switching off if you do it right at the 0 crossing, so right here. So the little detector, so to speak, that I built detects exactly that, the 0 crossing point of the AC, which comes out of the secondary of the transformer, and then transforms it to pulses, to square wave pulses, so either a positive or a negative pulse. In fact, it outputs both at the same time. Yeah? The reason why I built that mainly is because the frequency of the AC is very, very stable. So in my country it just happens to be 50 Hertz. But I know, and a lot of you know, that the AC frequency in the United States, for example, is 60 Hertz. Alright? So I did a quick calculation, which means that one wave of the AC, and there are 50 per second in my country, yeah, has a length of 20 milliseconds. Alright, so from this point here to this point here, this wave lasts 20 milliseconds. Now in the United States, for example, it would last 16.66 milliseconds. The pulse itself, which I generate with my little device, is at most 1 millisecond, but it can vary a little bit depending on the components used. But as a rule, I would say the pulse length is about 1 millisecond, which is not too long, not too short, and which is very useful to me should I, for example, want to build something digital which counts pulses, so which needs a clock pulse, say, yeah, and then you would have exactly 50 Hertz clock pulses, either negative or positive, depending on what you need or what you want, and they would be timed really accurately on the frequency of the AC you get into your home or your lab. Alright? As always, I try to keep it simple, effective, and cheap. Alright? So, let me place the camera at a better vantage point, and then I'll give a little bit of explanation of what the prototype boards really entail. Alright, they say one picture is worth 1,000 words. So I'm going to show you the signals I get from my detector there, from the 0 crossing detector, and then I'm going to show you the signals that I get out of the, you could say, a Schmidt trigger, or a signal amplification and cleaning up module, yeah, which contains the opamp and the transistor over there where I'm pointing at. Now I'll show you the signals and reference it to a sine wave below. So this is the signal I'm getting out of the detector. Alright, so there you go. So down below you see the sine wave. It's not a very clean sine wave, but I've got so much equipment going on for the moment that it's not a very pure sine wave. Either way, it illustrates perfectly what I mean by zero crossing detection. Alright, so the signal up here is the signal that comes out of the zero crossing detector, and I'll move one of the cursor lines to show you exactly where the zero crossing detector changes the signal it emits. Yeah, so you see I'm moving the cursor line to where the output of the zero crossing detector signal is. Yeah, there. Now if you follow the cursor line down, you see that it intersects exactly with the 0 point, or you could say the 0 volts point of the sine wave. Alright, so, and the second line shows you, of course, a second pulse. That's there. Alright, and as you see, it intersects almost precisely with the 0 point crossing. Okay, so this is the crude signal I get out of the zero crossing detector. Alright, so now let me show you, and as you can tell, as it crosses the 0, yeah, it drops extremely sharply down. Yeah, now let me show you what the signal looks like coming out of the opamp. So both signals are overlapping each other more or less, but I just, I want to show you how the signals look in reality. Alright, so what you see there, this very sharp square wave signal up there, is what the opamp makes of the signal coming from the zero crossing detector. And I'll move the cursor line, you see me moving the cursor line, and I'll move it to where the pulse exactly starts. There. So if you follow the cursor line down, you see that it intersects precisely with the center of the sine wave. Alright, now right down here you see delta t. Alright, so right here, delta t. Now look, if I move the second crosshair or cursor line, there. Now you see I have got exactly 20 milliseconds between both cursor lines. And what you see is that the zero crossing detector exactly detects the zero crossing of the sine wave. Yeah, so one there and one there. Right, so but these are the positive pulses. Yeah. Now I'll show you. Oh, by the way, for some of you, you might be interested. So this peak here is a 1 volt peak to peak, 1 volt per division readout, and let me see. So about there. Yeah. Yeah. We're at 1 volt per division. Okay. So 1, 2, 3, 4.5 maybe. So 4.5 volts is the peak. Okay, between these two cursor lines. So this line here and this line here. Alright, so the voltage between those two cursor lines is about 4.5 volts peak to peak. Alright, now I'm going to show you what the negative pulse looks like. Alright, so now what you're looking at is practically the exact reverse of the positive pulse I showed you a minute ago. Alright, so here you see the negative pulse. This is 0 volts, this is the negative. And we're still looking at 1 volt per division, so it's about 1, 2, 3 volts per division. 3 volts peak to peak. So at 1 volt per division. You could set it a little higher. Let's see. I think I am about around maximum. Let's see. I'm about maximum value here. Yeah, it's about as strong as I can make it. I could change its duration a little bit, but the amplitude is about as strong as I can make it. So there you go. So you get about a 3 volts negative pulse, alright, and it's synchronized with the positive pulse of the 0 detection. So there you have it. These are the 3 signals, the device outputs, yeah, the crude 0 detection signal, the positive pulse and the negative pulse. And yeah, and what I'm going to do now is going to transfer all the electronics to a perf board, and when that is done, I'll give you a little bit of explanation about how it really works. And thanks to the miracle of video editing, we're a few seconds later and all the parts have been transferred from the breadboard to a little perf board. There you go. And this is the whole 0 detection circuit. That's the underside of it. So a few tips that I want to give you is that if you're going to follow along with me, and you're going to use perf board like I did right here, once you've assembled everything, there are a few basic things that you need to do first before you really start to investigate whether it functions correctly or not. And the first thing that you shouldn't do is put in right away the integrated circuit you see here. Alright, so this is the LM358 dual opamp. And before you mount it back, you should leave it out, and you should set the voltage of the two voltage regulators. So the LM317, which in this case is this one here, and the LM337, so which is this one here. I set the voltage at 5.1 volts positive and 5.1 volts negative. Obviously you could set the voltages pretty much as high as you like or as low as you like, but keep in mind to have, let's say, decent functioning of the circuit, you will need about, I'd say, 3 volts minimum, either positive or negative. So the pulse length, in fact, is, let me show you, there. So the pulse length is, as you can tell right here, is 1.4 milliseconds. Okay, so this is the full wavelength, and the pulse represents only a tiny part of it. Before I move on building the next function for the power supply, a little explanation. Alright, so two trimmers you see here are for the voltage regulators. Alright, the LM317 and the LM337. And with these two trimmers you set the respective positive and negative voltage. Remember, the voltage comes directly from the rectifier module. Alright, so there's no stabilization or any other sort of manipulation of voltage. It's just pure rectifying and filtering. Alright, so then you've got 3 more trimmers, and this trimmer here influences the length and the shape of the pulse the actual zero crossing detector does or makes. It's based on a BC547 transistor. The transistor you see right here, in fact, okay, where my thumb is. So obviously if you're going to set the voltages and the pulse width and all that with the trimmers, having a scope, as you can tell, is a useful thing. Alright, so having a scope is a useful thing. It will allow you to set all the trimmers correctly. Now, if you don't have the luxury of a scope, I guess you could do it with a multimeter, but it will be a little bit lengthier and more involved to do so. But yeah, you could do it with just a voltmeter, and that would be it. Either way, using a scope, you could also set the initial pulse, which comes from the zero crossing detection. Then you can set with this trimmer the duration, so the duty cycle, you could say, of the pulse and its amplitude. And then with this trimmer you will set the amplitude of the negative pulse. Alright, so there are all in all 5 tremors to set. But either way, before you start setting these 3 tremors, remember you need to take or leave out the chip first and set the voltages first with these 2 tremors. One last detail, the chip takes a maximum, if I'm not mistaken, of 35 volts supply voltage. Alright, so never exceed that voltage. Alright, so after a false start, I should say, there you are, the finished double millivolt power supply. So, and I mean by that millivolt adjustable power supply, symmetrical of course, and stabilized. And there it is. That's the result. Now it may look a little bit strange at first glance, but before I get there, let me just explain in a few words what this is all about. So I intended to make a symmetrical power supply for capable of delivering, let's say, up to 50 milliamps, but with where the voltage is adjustable to within a millivolt. Okay, and to reach that goal, I made use of multi-turn potentiometers, so like the one you see right here. In fact, for the other side there's another multi-turn potentiometer here, and they have what is called vernier knobs, which means that for to make a complete revolution you need to turn the potentiometer knob several times. So there's a sort of a gear reduction going on within the knob. Alright? So, and that allows you to set the voltage literally within a millivolt. Okay? So, let me show you on the multimeter you see right there in front of you. So what you're seeing here is the positive output of the power supply. Alright, so I need to go below 2 volts to show you how accurately you can set the output of the power supply. So let me go to the 2 volts range. So there you see here, you can set the voltage up to 1 millivolts. Alright, so let's say I want 821 millivolts. Okay, so let's go down there. 821 millivolts. There. Okay, so yes, you can set the voltage within 1 millivolts. Now the reason why this fluctuates, you'll say, hey, but isn't the power supply stabilized? Yes, it is. But there's one caveat with this design. I'm using Zener diodes which start to regulate the voltage at the exact same level as the big power supply, so which is 56 volts. If you drop below that voltage, the Zener diode in effect will never stabilize the voltage, right? So to be able to demonstrate that it is stabilized, I should hook it up to the large transformer. But since we're still only in the test phase, I'm using a small transformer, a test transformer, in order not to damage any brand new parts. Alright? So trust me if I tell you that you can set the voltage to pretty much any voltage you want. So say I want 752 millivolts. Okay, let's do just that. Oh, 752 millivolts. There. Almost there. There. So yes, you can set the voltage pretty much to what you need it to be. So come on, 752, come on. Yeah, oh. Yeah, it's a bit fiddly, of course, if you want to set it to 1 millivolt. There. Okay, so either way, yes, well, there you go. 752 millivolts. Now, one of the questions you might ask is, yeah, but why would you want to be able to set voltages so low and so accurately? Well, there are certain electronic circuits where low voltages or very accurate voltages can be useful, and I'm thinking about, say, opamp circuits, triggering circuits, even amplification circuits. So yes, being able to work with tiny voltages, so below, let's say, 1 volt, or with voltages which can be set up to 1 millivolt accurately, has its uses in electronics. So yes, that's why I wanted to do that. Well, first of all, out of curiosity, how to build it, and second of all, like I said, in certain electronic circuits, being able to set very low voltages and very accurately are capabilities that can be useful. So yes, I built a power supply which is symmetrical and stabilized, which allows you to set either negative voltages or positive voltages, but up to a millivolts accurately, and also allowing you to set very low voltages, so meaning lower than 1 volt. Alright, so yes, that's the result. Now, some of you might ask, but why did you build the thing on a large print board and then on a tiny little print board next to it? Well, as you know, I'm using perf board to build my designs. Now, once in a blue moon, it does happen that the holes you see there, so through which you pass your components, do present a short. Alright, so I mean internally in the board itself. Right? It has to do with I gather the production method of these boards. Yeah. And once in a blue moon, like I said, it happens that one or more of these component true holes you see there short out within the board itself. A lot depends, of course, as usual, on the quality of the boards too, of course. I never had that problem, but I knew of its existence, so I knew it could happen. And unfortunately, Murphy's Law hit me right on. And, well, like I said, unfortunately for me, this particular corner of the board has at least one, or perhaps even more shorts in it, which forced me, after a while, to give up on trying to correct the problem on the board itself. And therefore I opted for a pragmatic solution, which is that I cut a tiny little board exactly to size, which could fill the empty space you see there, yeah, with all the components, in this case for the negative power supply. And it turned out okay. It works great, and the board performs remarkably well, as you can tell over there. Yeah, and I can set the voltage pretty much to any voltage that I like. Okay, so I'm turning the potentiometer. Yeah, there, you see? So I can set voltages low or high, pretty much as I want to. Yeah, so, and yeah, and it works great. So the only thing I will need to do is to fix this little board within that empty space there in a safe and electrically insulated way. Yeah, and that's it. It's not a very pretty solution, but it will work. So, if you're wondering how to build the millivolt power supplies, or well, I should say the millivolt settable power supplies, then look no further than the schematic of the big power supply, which is this schematic here, of course. And more specifically, for the positive millivolts or low voltage settable power supply, you should use the parts within the dotted line you see here. And for the negative power supply, you should use the components within the dotted line here. Obviously, all the polarities should be respected. So this is the negative rail, this is the ground rail, and here this is the ground rail, and this is the positive rail. Alright, so, and the output obviously is the emitter of the power transistor, alright, which is a Darlington transistor. Same thing for here. The output is the emitter of the Darlington transistor. So there you go. There are slightly different parts you need to use for the microvolt settable symmetrical power supplies, and those parts are indicated here. Now, see, there's a let's say a range of resistor values you could use for the load resistor for the Zener. Alright, so R3, or in this case R11. You will have to try out which resistor type or which resistor value gives you the best result. Alright? before we can end this video, I need to give you, of course, a little bit of explanation about how the zero crossing detection really works. And we start, of course, by actually detecting the zero crossing. Remember, the zero crossing is where the AC coming from the secondary of the transformer crosses the 0 volts and, of course, 0 amperes point. Alright? So, the actual detection of that crossing point is done by this little circuit you see here. Now, this is basically half-wave rectification. And what happens is that during the positive cycle of the sine wave, so the bump you see here, the little capacitor you see here is being charged up through this resistor here and through this transistor here. So in effect, the transistor acts a little bit like a switch. Alright? And since the capacitor has a very low value, its charge up time is really fast. Alright? We're talking about in the order of a millivolt or so. So during the positive cycle of the AC, the capacitor is being charged up. Now, as soon as there's a negative cycle of the AC, the transistor stops conducting. So in effect, you could say the capacitor is not being charged up anymore. But it will discharge itself through this diode into the source of the AC, so in effect into the transformer. It's a tiny discharge, okay? We're talking about at most a few volts. Yeah? So the capacitor will discharge itself during the negative cycle of the AC. And that produces at the collector of the transistor a pulse, as it were. So remember on the scope I showed you the output of the zero crossing detector itself, which is, you could say, like a square wave output. Yeah? Well, that signal comes from here. Now, technically speaking, you could use that signal as is for your own purposes. But for my purposes at least, that wasn't good enough. I wanted to have a really clean square wave pulse that I could use either on an analog or a digital circuit later on. And that's when this circuit comes into play, which is built around an opamp here. Now remember, the opamp we're going to use, well, that I use in the device, is an LM358. So in fact there are two op-amps in here, but I use only half of the chip. You're free, of course, to alter the schematic if you really want to and use, for example, a 741 op-amp instead. But, you know, the LM358 is really dirt cheap, and that's why I use this chip, and I use only half of it. Alright, so what happens really is that the op-amp is, technically speaking, is connected as a comparator, which means that you can set a certain voltage at which the output of the op-amp remains low at below a certain voltage, and if an input voltage crosses a certain point you set, then the output of the op-amp suddenly and very abruptly changes to a positive signal on the output. Now, and the output being on pin 1 of the op-amp. Alright? Now, obviously the magnitude or the amplitude of the output signal is very much a function of the power supply rail to which you connect to the op-amp, which in our case, remember, is set to about 5.1 volts plus. Alright, and we use an LM317 to do that. Okay, so the thing to remember is that you can set what people call a hysteresis, which means that by using the resistor R8 in the schematic here, to feed back part of the output signal to the input, and I think this is, if I'm not mistaken, this is the inverting input of the op-amp. You can set a certain range of voltage at which it remains either low or changes to a positive output. So if you were not to use this feedback resistor, the op-amp would change at a very precise voltage. But as we all know, due to differences in quality of components and all that, it would be extremely hard to set an exact voltage at which the op-amp would switch from low, so 0 volts let's say, to abruptly change to the voltage rail, so the positive voltage rail. And therefore R8 allows you a few, say, tens of millivolts, to set a few tens of millivolts, below which the op-amp, even if the input signal varies a little bit, the op-amp still remains at 0, and will only change to positive on its output, alright, when let's say the average of the input voltage goes above a certain voltage. Alright, so R8 you could say is rather critical. Okay, so the only other thing you should remember is that with this little trimmer here, you can set the level at which that changeover from low to high happens. It also influences the amplitude and the duration, you could say, let's say the duty cycle of the pulse a little bit, okay, not much, but you can set the amplitude and the duty cycle or the duration of the pulse within a few milliseconds and millivolts with this trimmer here. Okay, so basically that's what you need to know about this circuit here. I call it a Schmitt trigger because Schmitt trigger is exactly what I explained to you, something which stays 0 and then only changes to plus volts very abruptly if the voltage exceeds a certain threshold. Alright, but actually this is called more a comparator than a Schmidt trigger. The last thing you need to remember is that an LM317 can only take, if I'm not mistaken, up to 40 volts plus on its input. Okay, its input pin being the rightmost pin. If you look at the front of the LM317, the input pin is here, the rightmost one. It can only take 40 volts plus maximum on its input, and therefore you need to drop the voltage with R5 from, say, 65 volts plus to a little bit below 40 volts, and just to make sure. But of course that depends largely on the voltage that you will design your power supply to deliver. Okay, remember this voltage you see here comes from the rectifier board, so it's unregulated voltage. Okay, the LM317 will do the regulation. So instead of using a Zener, we're using an LM317. Alright, so to end it, the explanation, we still need to explain how the negative pulse is created. So how do we create the negative pulse? Well, you'll notice that in this little schematic here, I'm using an NPN transistor, by the way. So what happens really is that whenever the base of the NPN transistor gets a positive pulse coming from, remember, the opamp, which outputs positive pulses, it goes into conduction. And when it goes to conduction, there is a negative voltage coming from the LM337, which runs or flows through a resistor, through the emitter, and then back out the collector to ground. Alright? And that's exactly what happens. Whenever there's a positive pulse coming to the base of the transistor, it goes into saturation, is the word, so it starts to conduct fully and lets through the negative voltage to ground. Alright? And that's exactly what we pick up right here. That's where we pick up that negative pulse, and that goes out here. So basically the inverting circuit, as it were, is really very simple. Alright, so, and the most important part of it are these components you see here. So these 5 components here. So this in effect creates the negative pulse. This, remember, is an LM337, and it has basically the same limitations of a 317. So it can't take more than minus 40 volts, which means that the voltage which comes from the rectifier board needs to be dropped via this resistor here, R11. And it depends largely on what sort of transformer you use and what sort of output voltage you get. I mean, unregulated output voltage you get from the rectifier board. Basically the values for the components are listed here. Alright, for the 3 parts of the zero crossing detector I just explained to you, you see all the values here. for all the components. And R5 and R11, which are the resistors you see here, so this dropper resistor here and this dropper resistor here, yeah, those values can be anywhere between 400 and 800 ohms. I would say 1 watt is more than enough. Alright? Since we're never going to draw more than 50 milliamps, I would say 1 to 3 watt resistors are sufficient. The other parts here are pretty much what you need for the circuitry. I explained to you, with one exception. At a certain point in the video, I said I was using a BC547, and that is not true. I'm using a BC546. Alright? So, this transistor here and this transistor here are both BC546s, as you see here. Yeah? And that is important because a BC546 can take voltages up to 65 volts, alright, which a BC547 can't. A BC547 is rated to a maximum of 30 volts. So that's important. You need to use a BC546. I do use, for the zero crossing detector itself, very fast switching diodes, which is a 1N4148. Right? I suppose you could use standard rectifying diodes like a 1N4007 if you don't have anything else, but I would strongly advise to use 1N4148. So there you go. The zero crossing is explained, and that will end the video. So all I want to say now is thanks for watching, and I'll see you for the next episode.